This is Rick.
Okay. So thank you all for coming today. This talk is as much to sort of drum up some renewed interest as it is to pick the brains of some of the folks here, because I suspect that this particular set of simulations as we go forward are going to be kind of challenging. I want to explain the title a little bit, Blast from the Past. It's partly because we're talking about some very old ice ages, which occurred between about 750 and 630 million years ago. So it really is from the past there. And it's also a blast from my personal past, because I did a lot of this, the work behind this for my graduate research at Lamar Doherty. And as I was searching through some older slides, I realized the last time I had given talk about this here at GISS was in 2005. So there's probably not a lot of folks around in this room at the moment who would have seen that. So anyway, I thought I would start recapping by what I mean by Snowball Earth, or what the community has come to mean by Snowball Earth. You may have heard the phrase somewhere. It has gotten around, but there are some disagreements as to what this should actually involve in terms of environmental conditions. And in terms of why am I doing this now, resurrecting this sort of thing again now, it's partly because when we think about a world, the Earth this far in the past, with some of the unusual conditions that we're going to be talking about, we're essentially talking about something like another world. And that's particularly relevant then to folks who are interested in actually studying other worlds. We have some examples right here at home in Earth history. And ultimately, some of the things I'd like to do with a new set of simulations are the kinds of things that a group of people here are going to be working on incorporating into Model E. You may or may not have heard that there's a bit of exobiology funding here, and the effort has now gotten underway to tweak Model E into something that is going to be called the Generalized Rocky Exoplanet GCM, or GREP GCM. And ultimately that model should have the capability of modeling any planet that's sort of Earth-like. So part of the tasks there are doing things like changing planetary radius and whatnot. We're not going to go quite that far here, but there are some interesting considerations that cross boundaries. So, so first of all, getting back to what Snowball Earth is, or what we think it might be. Back when I was a graduate student, there had been this growing consensus that we'd had some terrible ice ages back in the past, and that was based in large part on this widespread distribution of glacial deposits that seemed to be of roughly equivalent age, and they were on just about every continent that we could find them. When we looked at these rocks, we see signs of things that look just like modern glacial deposits. So on the upper left, we have an example of a kind of rock called a diamictite, which is basically a mudstone with lots of larger clasts tucked in. It's the sort of deposit that you get when you have icebergs drifting overhead and dropping sediment off as they melt. And on the lower right-hand corner, we have an example of something that's called a sand wedge, which is a permafrost feature. And if you'll notice, there's sort of a V shape at the bottom. That's basically where the permafrost cracked successively over time, and every time it cracked, it made a little space down the middle for some sand to fall in. And over time, this whole thing widened into the wedge that you see. And you'll see also there's sort of a wavy surface across the top. That's another feature common to permafrost settings. It's called a thaw unconformity. So whenever you finally had temperatures warm enough to start defrosting the soil, you would get that sort of a layer layer, sort of wiping out the textures of the frozen soil underneath. And there are multiple generations of these sand wedges in this particular quarry that I visited. That deposit was laid down somewhere around 10 degrees away from the equator. So if you can think of ultimately continent-sized ice sheets sitting where, say, Saudi Arabia is right now, that'll give you an idea of how cold that environment seemed to be. So the width of that particular wedge is a little bit more than a meter. The subsequent generations are not as wide. And another hallmark of these unusual glaciations, apart from the widespread distribution of the glacial deposits, is that whenever the glacial deposits stop, they are capped by these very unusual limestones and dolomites, or carbonates. So they've been called cap carbonates for obvious reasons. And the assumption has always been that the carbonates would only be deposited once the ocean was warmer and you had the appropriate chemistry to precipitate out the carbonate. And these particular layers also have unusual carbon isotope signatures, negative del13C values of as low as -5, which is quite low. Usually you're talking somewhere in the modern a little bit above 0 per mil. So we have these things all over the place, and we had finally in the mid-90s some reasonably good evidence that yes, these were in fact low latitude deposits and not things that had been deposited at high latitude and migrated toward the equator over time. And in an immense volume on the biosphere of ancient Earth, there was a 2-page article written by a fellow named Joe Kirschvink, who's at Caltech. And Joe was asked to think a little bit about what the climate must have been like during these ice ages, as far as impacts on the biology. And so Joe thought a little bit about how you could explain, possibly, having such widespread glaciation, and he came up with this concept of a Snowball Earth, where if you had the continents distributed mostly in the equatorial regions, continents having a higher albedo than the ocean, you would precipitate some cooling, and eventually you would have lots of pack ice making its way toward the equator, and then you could sort of ramp up from there with a nice albedo feedback into a glacial condition. It's worth pointing out that the kind of scenario that he's talking about is not a totally frozen Earth. There's lots of ice, but there's also plenty of open ocean. So this 2-page article went unremarked for a while, and then in the 90s, as I said, once things really sort of got sorted out about, yes, we did have low latitude glacial deposits, and people were getting excited about really how do you do this. There was a new Snowball Earth hypothesis that was set forward, and this was described by Paul Hoffman and Dan Schrag and some other colleagues at Harvard. And they actually intended this particular Snowball Earth description, in which they envisioned a totally frozen ocean, surface ocean, to explain the geochemistry of those cap carbonates. So this was not a climatological argument. They were after trying to get some explanation for the isotopes. And as momentum sort of grew around the concept that they were building, they had another paper out in Scientific American in which they published this little graphic, and then that really caught a lot of people's attention, even those the folks who were not necessarily elbow deep in the field. So just to sum up here briefly, in the upper left, we have the first stage. So before glaciation begins, there's it looks like a normal Earth with a little bit of ice on land, but oceans are wide open. stage 2 has already gotten to the point where the surface ocean has frozen over. And so there's some ice on land, but there's a limited amount of ice that you can put there once you shut down the hydrologic cycle from having frozen over the surface of the ocean. Eventually, through volcanic outgassing of CO2, they imagine enough CO2 buildup in the atmosphere to reach a tipping point, basically, and trigger the thaw from the hard snowball condition. That's stage 3. And then afterwards, there's just an enormous amount of CO2 still left in the atmosphere, and so that explains going into this hothouse condition by which one can deposit those carbonates.
Was this still focused on the low latitude range? Is that what that was about?
The idea is to try to explain having glacial conditions there without tipping the planet over on its side, which was actually an alternative hypothesis for a time, but that was never terribly popular, and a number of people took a stab at disproving the plausibility of that particular scenario. So all the effort has basically gone into then, how do you explain something that looks like the Pleistocene on steroids? Advancing a little bit further from that original 4-stage diagram, once Paul and Dan got connected with Ray Pierre Humbert, and Ray did some modeling of his own, they got more sophisticated with the 4-stage setup, and they actually started assigning temperatures to all of these stages. And you'll note that at the lowest point in this graph on the right-hand side, global mean surface temperature is meant to be minus 50 degrees C. And the amount of CO2 required to get out of the current condition ends up being somewhere in their ballpark estimate of around 120,000 ppm. And to be able to accumulate this much in the atmosphere, they require this hard snowball because they have to keep the ocean carbon dioxide reservoir separate from the atmosphere, so the atmosphere has a chance to build up as this happens. Now, it has to be said that this is a really, it sounds so strange, it really captures people's attention. And so we did have a little media blitz after this. There was actually a book written about Paul Hoffman and his adventures, and a Snowball Earth BBC Horizon special that Mark, who's on Skype right now, Mark and I worked with the producers, and in the end, the show that they created was about 99.5% Hoffman worldview and 0.5% of the opposition. And it angered some colleagues of ours at Queen's University so much that they wrote emails to everyone saying never cooperate with anyone from BBC Horizon again. And so there was this rift going on in the Neoproterozoic community, which was not really extending to the wider world. So in 2006, we actually had a workshop in Ascona, Switzerland, where we got about 65 people together. There were geologists, there were biologists, there were climate modelers there, and we spent a week thrashing through a bunch of things. And at the end of that week, out of the 65 people, I would say 62 came away saying the hard snowball is dead. It's not possible to do, and there were a variety of objections based on evidence that people were accumulating in their own research. So, for example, having a hydrologic cycle that shuts down is not compatible with evidence for wet-based glacial activity. And the biologists kind of objected to having a totally frozen ocean so that light could not pass through to photosynthetic organisms. And you would imagine under those conditions you'd have mass extinctions. And although the fossil record is very sparse for this time period, there doesn't seem to be any indication of that sort of thing going on. And so, we could nitpick the hard snowball to death, but it's hard to get people excited about nitpicking. sort of stuff. So that's where the geological community stood in 2006, and it's where they remain. Geologists and biologists do not buy into the word Snowball Earth. So now shifting gears to climate modeling.
I thought the Snowball Instability was a typical feature of 1D energy balance models going way back to Ludico and Sellex, were those dismissed as nonsense by...
That's where Paul Hoffman got his original inspiration from, and also some earlier work by Jim Casting where they were specifically looking at not a Snowball Earth, but what if you had a runaway ice house condition? How do you try to get out of it? And so that's where some of Paul's numbers came from. Yeah, but here's a classic example of a problem when you have two communities that maybe don't communicate well with each other or as often as they should. And so, Paul as a geologist had some mistaken ideas about what he could understand from previous modeling work and apply to his conceptual model for Snowball Earth. And then once the geologists went through this and had their say and said, no, this isn't going to work, that information didn't really make it back to the climate modeling community. I got for Ron, in the corner there, a review paper of some of the Snowball Earth modeling efforts that have been done over the years. And it's interesting to note that the majority of them start with the premise that they have to freeze over the surface ocean. They absolutely must have this condition. And this drives how they design their simulations and move on from there. And it has led to sort of slightly bizarre explanations of how to account for glacial deposits in the tropics. They've invented these sea glacier phenomena where you've got pressure ridges from the polar regions managing somehow to shove ice along continental margins much further south, and it's just, it does not make a lot of sense. I had a discussion / argument with somebody once about, why, I can understand this is a really appealing and interesting intellectual problem, but why keep doing this if it's not really relevant to what actually happened in Earth history, if that's the problem that you're trying to solve? And they basically told me, well, that's not the problem I'm interested in trying to solve, I just think it's a neat issue. The difficulty there, though, is that when these papers get published, they talk about this is what happened, back in the Neoproterozoic, and that's not the case. So,
I have a clarification.
Sure.
Kind of going back to this continental configuration thing. If you look at the current planet and you look in the mid-latitudes, is the albedo higher in the southern hemisphere or the northern hemisphere? Because in the annual mean, it's cloudy all the time over the southern oceans. And when that first theory came out, they didn't have that knowledge. And so I just feel like everything we've seen up to now has neglected clouds.
It's not been a huge consideration. The main focus has been on the sea ice. It's really been the main focus of people's efforts. And that is something definitely worth delving into further.
But how do you constrain the cloud coverage in that time period?
I think a simpler question is this assumption about the continental configuration even necessary?
Well, there are, we don't have perfect knowledge of what the continental configurations were for each of these two glaciations, although one of them is more of a ring around the equator, and the other one is more southern hemisphere oriented. So you could run some sensitivity tests and say, well, what difference does it make? So that's one thing. But I think actually that particular aspect of the snowball has sort of faded into the weeds. Yeah.
I think just going back to Mike's question, there's also, when people try to do experiments about how to get out of Snowball Earth, there seems to be this disconnect between the simple energy balance models and then the GCMs. And so it just seems like the energy balance models are missing a lot of important feedbacks. And so they can't necessarily, be trusted, on other questions like how to get into Snowball Earth in the first place.
How do the believers, it seems no evidence for mass extinctions. That seems like a killer. I don't understand how you can even, that passes the giggle test.
So part of the effort to work around that is to then say, well, okay, there might have been some patches of open ocean, but then that misses the point that the hard snowball was intended to have this absolute separation of reservoirs so that you could get the isotope. So that's an issue.
How did they respond? They said the fossil record isn't good enough, or?
Paul himself, again at this particular meeting, by the end of the week, he must have been feeling a little bit beleaguered. He had started to back off a little bit and say, well, maybe there were refugia. Little open patches around hydrothermal vents or something like that. Or another an arc. Wouldn't have to be very close. Or that somehow you managed to create areas where the sea ice was not that thick and it was remarkably bubble free, so it would allow sunlight to pass through. That's been another idea that's been explored. So Paul was kind of defensive by the end of this week, and the very last question of the conference was asked by the organizer of Paul. So what do you think, about the hard snowball at this point? And he just turned around and said, "Oh, I believe absolutely it existed," and you could sort of hear jaws dropping all around the room. And I don't say this to be mean, but it was like, wow, okay. So the rest of the community will go on and do its own thing, and
that's the solution. Stop inviting these biologists and geologists to your conferences.
but the thing is, that really cuts both ways, because his point is he's trying to keep these two reservoirs of carbon isolated from each other so that you don't build up the cap carbonates, and so that's why he's arguing. So the burden is then on the people, on the geologists and the biologists who are skeptical and think there's a slush ball to explain, how you get this big isotopic departure in the end. So I think that's, both communities are really, have this big question.
So the alternative hypothesis for generating the carbon isotope excursion in the cap carbonates and actually just triggering the deposition of the carbonates is destabilization of methane clathrates.
It's always the reason everyone says.
Yeah, but there are actually in some of the cap carbonates you can find features that look very much like modern cold seeps. The diagenic facies is exactly the same, and a lot of the isotopic gradients are the same for the folks who have done the measurements. So again, the trigger into or out of this condition, what actually started this, we still don't know. But having this alternative explanation for dealing with the isotopic trends in the cap carbonates really opened everything up, because then you don't have to worry about keeping atmosphere ocean separate for millions of years. You don't have to worry about accumulating mantle of CO2 and making the ocean too acidic or whatever. It just doesn't have to happen that way. So then the alternative is then you have a slush ball. So yes, there was a really bad ice age, but we had lots of open ocean in the tropics and so forth. So moving on to some of the modeling stuff, I was in this up to my neck as a grad student in the mid-90s in terms of the field work, and I was just really puzzled by how do you actually do this? How do you get a climate like this? It's really hard. And my advisor, Nick Christie-Blick, managed to arm twist Mark into coming up to give a seminar at Lamont, and afterwards we sort of worked on him a little bit. So, maybe you could help him to do some simulation of Snowball Earth, because Mark had previously done the Jurassic for his own so in 1996, before I did my last field season, I faxed off a reconstruction of the continents to Mark, and we got started on our first set of simulations. And so in those days, Model E was not really even a twinkle in anyone's eye as far as I know. So we were using Model 2. For those folks not familiar, you know, this was the original version of the model that Jim used for his global warming experiments before he testified before Congress. So this was it's a coarse resolution, 8 by 10, 9 layers in the atmosphere, and at best we had a mixed layer ocean going with it. Now, as it turns out, getting ready for a paleoclimate simulation like this is actually an awful lot of work. You know, we've learned quite a few lessons over the years on what to do and what not to do, I suppose. And a lot of that will carry over into working with Model E. But in terms of boundary conditions, changing the continents around and the land-sea mass was a huge undertaking. But once that sort of is in place, everything else could just follow. So for vegetation, for this time period, you know, there were no plants on land. Plants on land don't show up until around 460 million years ago, I think, something like that. So we were, you know, at least a couple 100 million years before then. At best, there might have been some lichens or something like that on land, but that's really controversial. So we just assumed sort of a desert condition. Mixed layer depth of the ocean, the standard mixed layer depth was 65. We experimented with everything up to 4,000 meters, figuring that if the ocean was cold enough, basically have a well-mixed column like you do around parts of Antarctica, but all over. And for the initial sea surface temperatures, we don't have a reconstruction for that time period, so we just started with modern and decided to see where it went from there. Forcing solar luminosity, the sun was not as bright back then, so we dialed down the sun by about 6%. Orbital variations, we tried a couple different things, but it really didn't seem to make much of a difference. We did try a high liquidity experiment. We tilted the Earth to 60 degrees of liquidity, and the model ran for about 6 years before it crashed. And shortly before it crashed, we were seeing things like temperatures near boiling on the pole that was facing the sun. So really not a surprise that didn't work. Greenhouse gases, we still don't have a particularly good constraint on that, although we have a little more information these days than we used to. So we just started with 1958, and then we took 140 ppm as half pre-industrial and 40 ppm as sort of a low point. And we fiddled also with ocean heat transports, so increasing transports away from the equator and also reducing. Yes, so we can modify the strength of it. So this is representative of some of our first results. So these are two of the coldest runs that we attempted for the younger of the Neoproterozoic glaciations, which has the name Varanger or Marinoan is the other name for it. And somewhere along the line I've lost my scales on here, sorry. But it's easier to see from the snow and ice coverage on the bottom here that even with the coldest condition, CO2 down to 40 ppm, reduced solar, ocean heat transports come back by half, we still had a fairly large area of the tropical ocean that was not covered by ice. And we had, actually, Jeff made this nice little movie, time-lapsed, showing some of our earlier simulations. I forgot that I had this problem.
I did forget. I forgot how I did it too. So anyway, this will run to, I think, 60 years.
so even after 60 years, you know, nothing freezes over. And there's a poster downstairs actually that has a plot of all the temperature time series for the various simulations that we did. And it's quite cold for this scenario. I actually have a plot coming up where we can take a look. So that was the younger of the two Neoproterozoic ice ages. So this one was about 640 million years old. Then there's the other one that's 750 million years old. And Mark, if you can see this, I actually found your slides from AGU Boston, 2001. So again, this was similar to the other one, although here ocean heat transports were left alone, and we actually dialed down the sun a bit more than was appropriate for this time period, because we really wanted to push the model to see what would happen. And so here, and again, you can see that it's gotten quite cold, and as far as the snow and ice coverage, this was as close as we ever got to covering the Earth in ice, but again, this is not the appropriate solar value for this time. So we were having a hard time freezing things over. And just to show a few more compiled results from back then.
So I'm sorry, in the previous two slides it was 50% OHD. This one was 100%.
This was 100, yeah.
So was there any difference when you changed it to be the same? Why are you showing this?
I'm showing this because I found this slide. Sorry. Well, for the younger ice age, where I do still have a slew of those things, what ends up happening when you reduce the ocean heat transports further is that the open ocean area band around the equator gets narrower, but the heat is getting concentrated in there. So it's staying quite warm even though everything else is cold. And so this is just a comparison also of some of the different runs. So this is surface air temperature trends. So you're asking about the difference between 100% and 50. So if you look at the blue dashed and red dashed lines that are about midway through the plot, those have 100% OHT, and that bottommost dotted red line is 50% OHT. So it does make a difference.
Now, was the model at equilibrium at the time?
Yeah. So I mean, the earlier, the Ranger ones, we stopped at 60 years because that was as far as we could take it. It was just taking too long to get further than that. You know, with this same model in a GCM, I could reproduce these experiments in, you know, less than 12 hours. It was taking a lot longer then.
But I mean, is it true that it's only 30 years of this?
So really, I mean, even when I've run simulations out to 200 years, after about 60 to 80, there's no change. It's pretty much there as far as longitude is concerned. And this was just change in atmospheric water vapor over time. So yes, it gets extremely dry compared to the modern for any of these glacial periods. This was ocean ice cover. And so again, that red dotted line is ocean heat transports reduced by half. So that ends up having a considerably greater amount of ocean ice cover, but it's still not coming to 100%. Another plot, zonal average surface air temperature. So we're still left with this band around the tropics that's just not getting below freezing. So coming up to the modern stuff, and I don't have as much to show you as I would like, unfortunately, because I got stuck with a deadline and had to get that out of the way first. But what I wanted to do, and what I've been wanting to do for a while and never just got around to it, was trying to use the coupled ocean to redo some of these experiments and see how far I could get. So, you know, I was using Model E with 2 by 2.5 atmosphere, 1 by 1 1/4 ocean, and this version of the ocean has the fix to the Jet McWilliams bug. So it's not quite AR5 prime because it doesn't have some of the additional tweaking that Max has been doing on the code lately, but it does have that major ocean problem fixed.
What about topography?
So, for topography here, I was using modern geography because it not really sure how long it would take to get things functional. I mean, Jeff has now had a lot of practice because he did our Pliocene stuff, but that's still fairly close to modern. We were talking about something that's very different, and that would have been more of an effort than I wanted to do at this stage. So I stuck with modern geography, but we did change the vegetation again. So this time we changed everything over to something that was basically half bright and half dark bare soil. I took a spot in the Gobi Desert as an example of the proportions that I should be using. And this actually is probably a reasonable idea of what the landscape looked like back then anyway. You know, we know that there were some dune fields, but there really wouldn't be soil as we know it. Just be a lot of rocky outcropping and dry surround.
What are the albedo rules?
I have this written downstairs. Dark bare soils around 0.54 and the rest is light. Now we did look at a few different desert locations just to get a sense of what the range of variability was, it would be kind of interesting to choose a value, say from Western Egypt, which is much brighter.
Probably 40.
Yeah, I think even more. Australia has shrubs mixed in, though. I see.
Well, there's parts of it that could be clean here. It's pretty stark. It's probably 15. It's really tough.
Yeah. Well, yeah, it's the red soil. That's something that we could easily fiddle with, see what the difference is. And then I ended up doing a series of 7 experiments in total. One where I just took a copy of the E148 control run, and we changed the vegetation, so that was the only change there. And then there were 3 simulations each for the 2 glacial intervals. They had different reductions in solar luminosity. One was a reduction by 5.4%, the other one was by about 6.2. But then each of them had 140 ppm CO2 and 40 ppm CO2 in addition to 280 as a range. And so, I'm showing this as far as 70 years, which is a little bit less than the maximum length I got with the cold runs. And the first thing that popped up was a logistical issue. So having used the modern geography with lots of nooks and crannies in the coastlines, what I ran into was a problem with small MO. So the ice was accumulating excessively in some of the coastal grid cells, and so the model the first time the model stopped was actually in the early 1930s for the glacial runs, and then with some suggestions from Max, we implemented his expel excess ice thing, and I modified the GL melt file to extend the area of transport away from Greenland. What else did we do? Let's go right in my anyway, so we tried those things and restarted the model and got about another 40 years, and then the same problem cropped up in a new cell, but this time, instead of the west coast of Greenland, which was relatively easy to get around, it was in the interior of the Canadian archipelago, and I was not about to start fussing with trying to fix that particular issue. So I think maybe the next time I go forward with this, we will have some very simplified topography that's got much smoother coastlines, so we can bypass this particular problem. Interestingly enough, our quote-unquote control run, which was pre-industrial conditions except for desert as the land surface, got to about 140 years before it too tripped into the same problem of small and low on coastline. So it's not just the extreme conditions that gets us into it, although we get into this much faster.
Well, I mean, in the glacial periods, there was probably complicated terrain as well. Maybe this is a good opportunity to try and fix it in the model rather than just smooth things out. Huh?
I think that Allegra has run into this on occasion. Usually, for her, it's in the coastal cells that are very shallow, and that's true of the Canadian archipelago cell that I had a problem with the second time. But the west coast of Greenland was actually quite deep, and it was still running into this issue. So
Can
now
you describe it for those of us who don't understand? I don't know what MO means.
Small mass of the ocean, so there's not enough water left in the cell. There's too much ice.
Yeah, I think there's a feature of Model E that basically you cannot freeze the ocean to the bottom. You always have to have some water there. And until it is fixed, I guess you cannot do Snowball Earth at all, because eventually at some point it will start to freeze to the bottom, and that's something that is, I guess, in the algorithm. Well, it was several years ago. I don't think anybody has fixed it. Maybe somebody
Yeah,
did.
and this of course, since this is not quite AR5 prime, and AR5 prime itself is still waiting on the fix from Andy and Valdar to the radiation, so that it's not too excessively icy. I mean, I think we're just having an extra problem built in here also. Oh, now I remember the other thing I turned off at Max's suggestion, and Igor told me how to do this, was to turn off the limitation on how much snow is building up on land, because that was probably also contributing to this push of super cold melt to the coastal regions and making the ice accumulate a little bit faster. So one of the things that I thought was kind of funky about this when I plotted this up, I was really not expecting. So you'll see there's of the two lines that are near the bottom of the graph, there's one that looks like a bunch of yellow dots on top of red. What you can't see there is a blue line, and those are the bottom three runs that are listed in the legend there. Those are all the younger ice age. And so again, the difference between them being the amount of CO2, which is progressively less, goes from 280 to 140 to 40. And right now, all of those trends are basically plotting one on top of the other. And the same is true for the older ice age, which is the colder one underneath. You can just barely see a bit of blue poking out from underneath the green, but it's the same issue there.
The same change of CO2?
So it's the same changes in CO2 progressively, and it's just that the lower curve there, those three runs have a further reduction in solar luminosity. So that explains the cold, the fact that it's colder, but I was not prepared for these runs to be so similar to each other at this point in time. And so just a couple of quick maps here. So this was the difference between the coldest of the older glaciations. So this is the maximum solar reduction, maximum CO2 reduction, compared to our modern no desert control. And so it's really gotten much colder in the north polar regions, and that's, I'm sure, related to the problems that we ran into with the ice. And for snow and ice coverage, I mean, again, we're seeing the same thing here. I think the expanded GL melt around Greenland probably helped to push the ice front further south, and so that's where we've got so much more popping up over here. And then this is the younger ice age, so not quite as severe reduction in solar luminosity, but the same CO2 difference. This is 40 ppm versus the 280 in the control, and it's a similar pattern, right? Lots of cooling in the North Polar region and that big front south of Greenland, and you can see that reflected in the snow and ice also. So, I mean, going on from here, there are a lot more things that I want to dig into, but I would very much be interested in hearing people's suggestions about ways that I might try to bulletproof the next set of simulations against running into problems so early. I know that Allegra has talked about her last glacial maximum runs needing close to 1,600 years to come into equilibrium in the deep ocean. I can imagine that these would take a lot longer if I wanted to get that far, but I need to be able to sort of get that far. So, so any thoughts about stuff that I might try with sea ice or anything?
Well, this doesn't really solve your technical problem, but you can do something very idealized where you just put a rectangular continent on the equator, and then you talk with Bob Fisher, who's doing like a continental land ice model, and it seems like that's a really well-posed problem that you could do just as a sensitivity test.
As a sensitivity test, yeah. I mean, ultimately, I would love to get to the point of having the realistic continental distribution and topography built in. Because I really, there's just so many questions with these ice ages about, where do you nucleate the ice sheets? How do they get started?
But it seems like you're trying to do like an even lower order problem than that. You're just trying to say, can I basically freeze over the planet? And you're basically starting kind of arbitrarily with modern day technology, topography. And it seems like I can't see that it's any worse just to try something that's idealized, and even though it's idealized, it seems like it's a better approximation. Also, you could bring in land ice just from Bob again. I think that's something that you don't know much about the topography, but maybe you just assume something really simple. Just assume there's no topography at all.
We've done that. Actually, so for the older experiments that I showed you here that we had done previously with Model 2, the results that I was showing you were from runs with uniform 50-meter topography. We did have a set of runs where we introduced mountain ranges to one of the configurations and looked at some differences there.
I mean, I just feel like one of your technical problems right now, the ice forming in base, is just because you've done a really specialized problem that in some ways doesn't resemble what you want to do anyway.
Yeah.
So you could just, at first I would just suggest just trying to do an end run around that problem.
Okay. Some of the other things that ultimately I would love to do, which almost nobody has done before with Snowball Earth simulations, probably because it's not that easy, is take advantage of the modifications that the GREP group is introducing. So to do things like be able to change the length of day, which was shorter back then, about 21.9 hours instead of 24. And only one person I know of has ever done, the sped up version of these glaciations, but they did it with the Genesis GCM version 1, and nobody's tried it since. So to do something like that, to be a little more sophisticated with the solar luminosity. So Mike, one of the things that Mike is interested in pursuing is changing the spectrum also, and not just the intensity, and getting that right. And one of the things that was actually built into the original Mars GCM that Mike worked on, and that I know the group is also trying to get into Model E for the purposes of being able to do Mars appropriately, is the ability to condense CO2 from the atmosphere when it's cold enough. And we did have indications from our runs that seasonally in the polar regions it should be cold enough to be able to do that during the snowball. So it would just be nice to have that additional level of realism, because
sort of do this, but can you explain why, in the, sort of Siberian area there was no change in snow and ice coverage? I mean, it was, yeah, sort of no change or a little bit lower. It seems like a very strong band in there.
Maybe already, it was just, it had it anyway, so there's no change.
Well, you
Maybe-
remove the vegetation, right?
Yeah.
And this is compared to what is your reference control?
So the reference here is actually the no vegetation. So these are both no vegetation. The no vegetation, and I'm sorry, I forgot to put this plot in the slide. The no vegetation run compared to the regular pre-industrial control is about a degree or so cooler. But I didn't have maps and change in distribution of snow and ice cover. It may be here that in some of these locations that it's just already dry enough that they're not transporting.
For no vegetation, it's quite possible that most of Siberia will stay covered by snow even with modern radiation and everything. Because we have this problem in the model already.
The perma-snow, right?
Huh?
Perma-snow.
Yeah.
Max came to discuss the perma-snow.
Yeah.
It's a vegetation problem for the current period of snow. I mean, definition of vegetation.
Linda, can you hear me?
Yes, I can hear you.
Do you know whether or not with the experiments that Jim did using Gary's model recently, where he used alternate values of CO2, including some really low CO2 values, was that with Gary's fully coupled model? I think it was.
Yes.
And so
Yes.
he must have had some of these same kind of problems that you ran into. Maybe he has solutions.
He may. Tony mentioned that that they got a hard snowball solution at 1/8 modern CO2. But that paper isn't in
Gary just sent me the paper last week.
Okay. So I'll need to talk to Gary about that.
Yeah, it would definitely be worth it because to the extent that the problems are with the ocean model, I mean, it's essentially the same ocean model. So he may have, I'm sure that they're just workarounds, but he may have workarounds.
And didn't we have that one thing we used to do where it would flip something to land ice, that it would change the surface type of it from
Yeah,
carbon
that's
to fluid?
no, that was with respect. That was with the Qflux model where when you were freezing to the bottom of the mixed layer, you essentially didn't know what to do with it at that point. With
Right.
I mean, you might run into the same problem where you are running freezing to the bottom of the ocean. I mean, that might be a similar problem, but I don't think if we could avoid such a screwy workaround, we would prefer to do so.
Well, the problem with that in Model 2 and the Qflux is that lots of the coastal cells would freeze to the bottom
Right.
and they'd convert to land, but then your diagnostics for what's land versus what's ocean get screwed up
confused,
because
yeah.
it doesn't keep track of you. So,
What do you do for droplet concentration? We have this really, the model has a very kludgy kind of base state, which is the continental clouds are 170 droplets per cubic centimeter, and ocean, I forget what they are, 60 per cc or something.
I have not touched that.
I think you could have a lot of liberty with that. You could say droplet concentrations of 50 everywhere, or something like that. That would give you darker clouds, that would help.
That would be interesting.
Because I mean, I don't know why droplet concentrations are higher over the land, but I would think it has something to do with people over the land and maybe vegetation over the land. So,
Yeah, and if that is the reason for it, then sure.
Another reason for making the effort to put in a realistic continental distribution for the time periods that you have geologic evidence is because you do have a fair amount of evidence of the glaciers on land as they reach sea level. And one thing you could sort of check, do a comparison between the model
want to be careful to avoid as much as possible the assumption that that's the point that I have to aim for. Because I think that's what a lot of the more recent modeling efforts have had as a focus. You know, we need to have this goal, and we'll do whatever we need to get to this goal. I want to avoid doing that. And if it happens to fall out of the way the model is operating, and I do need to talk to Gary about this, then for me personally, that would mean maybe we need to look and see if the model is doing something okay, because although the geologic evidence is not as abundant as looking at the Pleistocene, I have some pretty strong confidence in the things that we see there.
You can have both. You can have both goals in mind when you sort of set up a series of experiments. There's the one goal is to simply put in as accurately as you know the various forcings. And in our experience, and with a lot of coupled ocean models that have tried this, what they find is that you don't get a hard snowball solution for the best known forcings. But you can continue on and say, okay, well, how far do we have to push this to actually achieve the hard snowball Earth solution? It gives you a point back in time and it gives you various things that you can make assumptions about with regards to the early Earth and more importantly the other planets as to the conditions that where you would find there are hard snowball planets. So exploring the full range all the way down to a hard snowball solution is interesting, and somewhere along that path you would be saying, well, at the mirror no one hears what we believe the situation was.
Yeah, except that for most of Earth history, we don't have anything close to a snowball. So I think there are enough people who are taking care of the angle of how far do we have to push a model to get to a hard snowball solution that I don't want that to be a first focus. I want to try and drag it back to reality.
Well, we're looking at a proposal.
Yeah, I know.
To be written, and that proposal specifically is early Earth and exoplanets. So.
No, not the way this proposal has to be written. No. Yeah, it's there's a difference in focus for doing Snowball Earth specifically. That gets away from talking too much about exoplanet relevance, although that certainly gets built into what we include in it, because it will work for both circumstances. Anybody else?
Well, what is it about the Neoproterozoic that's different from the rest of Earth's history?
So the bit that's of real interest is that although the fossil record is very sparse, this is around the time when we first get multicellular complex life. And so there's been lots of discussion about, does the extreme climate drive evolution one way or the other? And it's really hard to address that question if you can't be more concrete about what you even think the conditions may have been. Well, no, this is much later. Yeah, Metazoic.
My question is, why do we have Snowball Earth only during that 100 or 200 million years? What is it about?
There is one older event at around 2.1 billion years, and the kind of interesting thing about these events is that there seems to be going on at the time some reorganization of the chemistry of ocean and atmosphere, which may be biologically driven. With the 2.1 billion year old Snowball Earth, in some respects it's a little easier to make the geochemical and biogeochemical arguments.
Is that the rise of oxygen or something?
To something more than a negligible amount. It's still quite low until after the
But you said it was at 2.1 million, you said it was after the great oxidation.
2.1 billion.
Okay, so it's after.
So there are glacial deposits interspersed with the iron formations. So
There wasn't one before the great oxidation. Earlier than 2.7 billion years. Was there? No.
I think there's speculation that there might have been one
Yeah.
at 2.7 or 2.8 roughly.
You're working
2.8.
when you get that far back, you're working with such a small section of the geologic record because the rocks just aren't preserved that well, or to a great enough real extent that it's part of the reason why a lot of the discussion that far back centers on the chemistry, because if you assume global ocean chemistry, global atmospheric chemistry, it's easier to make progress. Whereas by the time we get to the rocks that are the age of these Neoproterozoic glaciations, and you saw that map with the dots all over the place, there are actually a lot of places where you can go look at rocks of the relevant age and think about what they're telling you in terms of the depositional environment and the processes that generate it.
We've got a lot more serious problems when we go back that far down because the solar constant is so much lower. We have no idea how we weren't glaciated.
Yes,
There's no solution.
Not yet.
So-
It's an
But
interesting
not
question in the other
94%.
direction.
The glaciation.
Yeah.
Well, we
94%.
we don't know because we don't know. We know that it wasn't, but we don't know why it wasn't glaciated over. That's the point.
Yeah. Yeah.
I thought when we went down this like way back, but 94% luminosity, you have a problem?
No, I don't know about 94% luminosity. If you go back farther,
Yeah.
then you're going to have serious problems
Yeah, there are serious problems.
that we don't know. People have all these ad hoc solutions.
Clouds.
Why not? How many droplets?
50.
Anybody else? No, thanks for
so
coming.
much.